Next up, we have Rachel Robey from the University of Colorado Boulder, who is in applied math. Her advisors were Keith Julian and Ian Grooms at Oak Ridge National Laboratory, and she will be speaking to us about approaches to multi-scale challenges in measurements and modeling of geophysical flows.
Hi, so thank you, and thank you for being here to hear about some of my work in geophysical fluid flows. So I've had the privilege to work on several different topics in this area through my graduate career, in no small part because of the CSGF, for which I'm very grateful. Before I begin, I want to take a moment to acknowledge and thank some of the incredible mentors that I've had along the journey, and I've listed some of the different topics I've worked on. For the sake of time, I realized it was a bit too much to try to cover multiple topics in 15 minutes, so today I'm just going to focus on talking about remote sensing wind LiDAR and the work I've done looking at these instruments with Julie Lundquist. So wind LiDAR have really grown in popularity and come into their own over the last decade. They're a remote sensing instrument. I've shown one here. And compared to maybe more traditional approaches, like erecting this 100-meter tall meteorological tower equipped with expensive and sensitive instrumentation, you'd imagine that it's a little bit more economic or easy to deploy in the field. And so it's really grown in popularity, not only for academic field campaigns, but we also see it used in industry, and the wind energy community in particular have embraced this as a way to measure wind fields. But what is LiDAR? So the pulse Doppler LiDAR that I've worked with operate on the principle of measuring radial velocities of the winds by diagnosing the frequency shift in light when it's scattered off of these naturally occurring aerosols that are moving along with the flow. And so we target multiple distances along this light beam to make retrievals. And the key point that I want to make here is these are remote sensing instruments. So when we get a retrieval, it's not a point measurement. It's really a reflection of an average of returns on a probe volume on the order of tens of meters along the beam. And so compared to these sort of traditional in situ instruments, where we're making measurements on the order of maybe centimeters, we're suddenly talking about probe and scan volumes on the order of tens to hundreds of meters. So they're similar to active dynamic scales in the flow. And as a consequence of this, we have a complex component of the error that's going to depend on the variability of the flow itself that we're trying to measure. And this is hard to get a handle on because the flow is complex, and it's a moving target. So it's going to vary site to site, and it's going to be continuously changing and responding to conditions. So this is a great opportunity to use simulations of the flow field where we have a full knowledge of the winds and look at how that's then processed through a model of the LiDAR observation system. So this lets us understand not only what the error looks like, but what conditions and mechanisms are giving rise to it. And that can inform how we want to design future scans, and also how we want to interpret and be processing the data. And so we looked at a couple different use cases for LiDAR. So the first one is profiling LiDAR, and these are meant to return a vertical profile of 3D velocities, much like we would get from a meteorological tower. And we do this by making samples with the LiDAR beam at an incline where we make stops around this cone as shown. So we're talking about moving the beam on a cadence of about 1 second, and for this DBS scan, we're stopping at the cardinal directions around the cone. And we'll use these measurements to reconstruct a three-dimensional velocity. And so we can kind of put together a basic model for how our virtual instrument is going to sample the modeled flow field. But this is also useful for giving us a framework for how to think about how the observation system is filtering the actual flow. And so just kind of briefly, I describe how we sample the simulated flow, where we make the retrievals along the beam. But then the key point for the profiling LiDAR is that once we have these radial velocities, we need to reconstruct our three-dimensional velocity. And so we make an assumption that at a given height, all of the radial velocities are projections of the same velocity vector. And this lets us have enough spanning vectors to reconstruct the wind velocity. But effectively, what we're doing here is that we're assuming that the winds are constant across the scan volume that's on the order of tens to hundreds of meters across. And of course, the atmosphere is turbulent. That's not really true. And we're not expecting this to be met at any given instant, but that if we have quasi-homogeneous conditions, that if we take a long enough time average, we can dampen out these variabilities and get a robust measurement of a mean wind. But typically, we're a bit hand-wavy about this. We say we take a time average. There's kind of cultural norms about what time averages are normal. So we wanted to get a more nuanced, kind of mechanistic idea about how turbulence is causing error in these measurements. And so to do this, or get an idea of what this looks like, we run large eddy simulations with atmospheric boundary layers. These are idealized simulations where everything's flat, periodic, and so the only source of variability is from atmospheric turbulence. And so we run these with the weather research and forecasting model, and we do it in 3 different kind of turbulence regimes in the atmosphere. So we have a couple convective cases where we're heating the surface, and this creates large convective plumes that are mixing and creating these large boundary layers. And for a stable layer, where we have density stratification that inhibits vertical motion and gives us kind of a different character of turbulence. And so we can see in these kind of these vertical cross sections an idea of what this turbulent structure might look like. So in a convective case, we have these large convective plumes, versus a stable case, we have much smaller mechanically forced kind of structures. And I've superimposed the LiDAR scanning geometry, so it's not hard to believe that this sort of fixed geometry will have a different filtering effect and interact differently with these very different regimes of turbulence. And so by running ensembles of the virtual instrument within these domains, we can start to get an idea of what the distribution of error looks like in these different turbulent regimes. But along with these virtual measurements, we have this framework as well where we can understand, if we view the turbulent variations almost as random variables, we can propagate that variability through the whole system to produce an error that's based on that turbulent variability. And so this lets us have a more mechanistic view of what's coming out of the virtual measurements. And the LES, while giving us the virtual measurements, is also giving us an idea of what these distributions look like, for the turbulent variations. And so we can do that for the raw reconstruction and also for commonly derived variables like the horizontal wind speed. So I show the estimated error distributions for the horizontal wind speed, and this is before taking any time averages, which is why the values look quite large. And so this is at different heights in the strong convective boundary layer and the stable layer. And we can see there's some pretty marked differences between different turbulent conditions, but also with height within the same turbulent simulation. And we can track this back then to what's driving the error. So in particular, for the convective case, the projection of the variability of the vertical velocity is overwhelmingly the driving force for error when it's projected onto these inclined beams. And so this gives us a benchmark for kind of what these quantities are starting to look like, but also hopefully gives us enough an idea about the mechanisms and the framework of what's happening to then take that and start to generalize what it might look like in a wider range of scenarios. So when we're thinking about scan design and the elevation of the beams, there's not going to be a universal best answer, but we can start to think about how that affects the filter scale and how that affects the projection onto the beams. And it can also inform how we need to treat the data. So for example, longer time averages will be needed in the strongly convective case, where we have larger errors and longer decorrelation times compared to a stable case. So we can start to have a more nuanced view. So we also looked at other kinds of use cases for LiDAR. So as opposed to the profiling LiDAR, we can kind of take a unique look at the atmosphere where we start to measure slices through the atmosphere. And this lets us capture the spatial structure of dynamics in the atmosphere, much like we might think of like Doppler radar, where we're looking at the weather. We can spatially resolve some of these structures. And so we looked at a field campaign in Portugal where winds are moving over these 2 parallel ridges. And so there's 2 LiDAR in a transect with a wind turbine that get to capture the wake of the turbine in this transect plane, along with some LiDAR that are collecting these vertical slices of an unwake transect. And so we can start to look at how this measurement process might distort the wake that we're retrieving with the LiDAR versus what is actually existing in the flow. And so we can look at actual data from the field campaign and sort of these beautiful captures of a resonant mountain wave over the ridges with recirculation during the case study, and also captures from the LiDAR in the wake transect capturing that wake as it propagates across the ridges. And so in order to simulate this, we have a real case, and we can use this sort of paradigm of mesoscale to microscale coupling. So following some work validating simulations at this site, we use global reanalysis data to force a mesoscale model, and then we nest all the way down to this finely resolved LES of the site during our case study. And so this gives us a realistic representation of the flow during the case study that we're looking at with data to kind of get an idea of how the observation system is working on flow of this type. And so similar to the profiling LiDAR, we can create a fairly simple model of linear operations that the flow is being filtered through when the LiDAR is observing the wake. So we have an instrument in the valley and on the downwind ridge looking up through the transect at the wake. And we are filtering through this sort of probe volume, but also we're looking at the projection onto the beams and the time that it takes for the beam to sweep through its scan. And so this lets us, again, break down how we're contributing to errors in our horizontal velocity measurements. But we can also look at how these measurements are distorting how we view the wake as the structure as a whole and its behaviors. And so we can go ahead and fit for the underlying true wake, but also for the virtually measured wake. Quantities like the magnitude of velocity deficit in the wake, where the center of the wake is and its trajectory over its extent, and the vertical extent of the wake. We can see that there's definitely variations, although we capture it as a whole well, there are variations in the measured wake compared to the actual true underlying simulated flow. And so there's some really key areas where we see that occur, although we get the trajectory really quite well. We're dampening the magnitude of the wake significantly, and we're blurring out the edges of the wake, making it appear wider than it is. And so these are key variables that we might care about when we're thinking about the dissipation of wakes and how they might interact with other turbines. And because we can also track back where these errors are coming through, we can make recommendations like that we want to increase the density of our retrieval points in the wake, and that this is a low-hanging fruit way to then improve the accuracy of our wake retrieval compared to things that we can't necessarily change about the measuring process. So in all of this work, it gave us tools, but also I think insights and reframing of how we think of the measurement system compared to what the community has been doing. And this has been a springboard into contributing to some collaborations, looking at different ways of using LiDAR. So looking at upwind blockage in front of a wind farm, but also different scan designs and profiling LiDAR in more complex conditions, again, using those set of Pertigao simulations from the field campaign. All right, so with that, I'll take questions.